Our quiz was find log base 4 of 16, log base 7 of 7 to the 3/5, then solve 2 to the x equals 12, 3 to the 4x minus 5 equals 6, e to the 2x equals 9. Now, people did on the homework have a little trouble solving these equations, and it's really quite simple. But you got to, once you pick up on it and know what the conversion is, it's not difficult at all. Okay. But it's difficult to get the hang of it. So we'll work on that a little bit. Okay, so we have log base 4 of 16. What does that mean? That means what power do you raise 4 to in order to get 16? Okay, now there's an equivalence here. Log base b of c equals a is equivalent to b to the a equals c. So this tells you that a is the power you got to raise b to in order to get c. Okay. If you get used to that, and I remember when I learned this stuff in high school, I had to keep repeating it to myself. It didn't pop into my head complete, okay? I had to do a bunch of problems until I got used to the idea. I probably would have done better if somebody had just given me this equivalence, and I would have gotten used to it. But not everybody's was thinking the same way I was. So the way it was taught, I mean, I had good math courses, so no complaint. Okay, but if you look at this, log base 4 of 16 equals, we'll call it A. That's in the form log base b of c equals A. C is 16, so equivalent is b to the a equals c for the a equals 16. You can formally start from this and come down to the question, okay, you got to find what power of 4 equals 16. Okay. Or you can just get used to it and say, this means 4 to what power equals 16? Now here I'll say clearly, A equals 2. Since 4 to the second power equals 16. Thus, log base 4 of 16 equals 2. Now, everybody got that on the quiz. I'm just trying to connect it to this thing that you're going to need to solve these equations. Okay. Now, if you apply the same thinking, again, log base 4 of 16 equals 2 means 4 to the second power equals 16, right? If we look at log base 7 of 7 to the 3/5, we don't necessarily want to go through all this identifying A and B, but we could. We could write log base 7 of 7 to the 3/5 equals, we'll call it A, because that agrees with the form that I've got here. Now, you might be using a different form. The forms are the same in the text, in all texts. Okay, but sometimes there are different letters used other than A, B, and C. I use B for the base, then I just use A and C arbitrarily for the other numbers or the other symbols. Okay, log base 7 of 7 to the 3/5 equals A means 7 to the A equals 7 to the 3/5. Okay. So A equals 3/5. Log base 7 of 7 to the 3/5 equals 3/5. And maybe we have the right sense because it would be just an obvious identity. Okay. So you want to think a little more on that. You want to get used to thinking about it. But it was good at the first one. The second one almost looks so weird that you can't solve it, but it's the easiest one. Okay. Now I'm going to solve 2 to the x equals 11. Okay, so we have the equation 2 to the x equals 11 is b to the a equals c, if b equals 2, a equals x, c equals 11. Now this is exponential form. Log form is log base b of c equals a. So log b is 2, log base 2, c is 11, and a is x. So x was log base 2 of 11, log of 11, divided by the log of 2. Now, you have to use your calculator to do that. And I would use the fact that it's log of 11 over log of 2. Your calculator allows you to dumb yourself down by just doing log base 2 of 11. Okay? Make yourself a little smarter by using this rule because it's an important rule. And that's going to come out about 3.6. Big question mark on that because I did it in my head. And I think actually now that I'm thinking about 8, 16, yeah, it's 3.5, 3.6. Okay? Punch it in your calculator. I don't think I'm off by more than a tenth. But my brain is working real well this morning, so double check me. Okay? Now, you can go back over the video I made last time, or video from Open Math, or video from anything, okay? Or an explanation from some AI. The caution I make about using AI is don't use AI to get the answer, use AI to understand. If you're content just to get the answer, it's going to dumb you down. Okay? You're not going to be as smart as you could be, and you're not going to do as well on tests either. But as far as just your overall ability to think through things, make sure if you use an AI or videos or anything else, that you strive to understand what's going on so you don't need to refer to. Okay, so 3 to the 4x minus 5 equals 6. Okay, what's the form? This is the form. B to the A equals C. B equals 3. A equals 4x minus 5. And C equals 6. So equivalent form is what? It's log base 3 of 6 equals 4x minus 5. Now, as I said in the video last time, log base 3 of 6 is just a number. Just treat that as a symbol. Let's put this in the form where the x is on the left, log base 3 of 6 on the right. 4x minus 5 equals log base 3 of 6. People like to add the equation 5 equals 5, or say plus 5 equals plus 5. And when we add these two equations, we get 4x equals 5 plus log base 3 of 6. And then we divide both sides by 4. So x equals 5 plus log base 3 of 6 over 4, which equals 5 plus the log of 6 divided by the log of 3, all that over 4. And at this point, you can enter that expression in your calculator. Then you want to check it to make sure you entered it correctly. You want to plug your result back into the original equation. You're going to get 4x minus 5 is about 1.7. So it'd be 5.7 over 4, about 1.4. What do I do? Yeah, if x is 1.4, then 4x, that'd be 3 to do. Yeah, I'm trying to do this thing in my head, and my head keeps forgetting what it just said. Okay? Just one of those mornings, sorry. It looked to me like 1.7 power of 3. So 4x minus 5 would be like 1.7, 5.7. Still get it. It's not right. Okay, something wrong with my mental arithmetic there. All right, you get the idea. The idea is simply, if you don't know what to do, always go back to this form, this equivalence. It always works. It always works if you have an equation in this form or this form. Now 2 to the x equals 9. Dispose of that one pretty quickly. This is equivalent to log base 2 of 9 equals x. So x equals log base 2 of 9 equals the log of 9 over the log of 2 That's going to be approximately 3.2, somewhere between 3.1 and 3.2, I think. Okay. And that's easy to check because 2 to the third power is 8. And 9's just a little bigger than 8. So you need just a little bigger power of 2 to get 9. So let's just do kind of a check. Is 2 to the 3.2 equal 9? Well, 2 to the third equals 8. Need a bit more than 3 for the exponent. $3.2 looks plausible. So do a little more work on that if you're having trouble with it. Now, there's another type of equation that you might run into, but I don't think you're going to run into it until you get into the homework that's coming up. And I'm going to pause for a minute and double check recording, but it doesn't want to do that. Okay, now I just did all this without recording. Everything else was recorded. So what we want to do is graph y equals log base 3 of x. Now the whole thing is very straightforward, so you don't really have to watch me do it in detail. It's very simple. We start with a table of, well, we start with a table. This is the function that's inverse to the y equals 3 to the x function. So we start with the 3 to the x table, which is very straightforward. I don't have to explain that to you. And then we get the inverse function by swapping columns of the table. This should be a familiar operation. We swap the roles of x and y. And we get the table for log 3. We notice that the biggest value of x is 9. So we set up a set of coordinate axes. We go out to x equals 9. We don't put much to the left of the y-axis because there are no negative x values. Then we are going to need values 3. Well, okay, we got x equals 9. We're going to need x equals 3, meaning we divide the interval from 0 to 9 into 3 equal parts as best we can. It's a little tricky to divide things into 3 equal parts. I never get it right, but there it is. So we have x equals 9 here, x equals 3 here, and x equals 6 here. Then we're going to need x equals 1. So we take the interval from 0 to x equals 3 and divide that into 3 equal parts. So here you have 2 lines that divide this interval into 3 equal parts. And the x equals 1/3 line is the one closest to the y-axis. And then we're going to need 1/9 of all things. So we divide the interval from 0 to 1/3 into 3 equal subintervals using these 2 little dotted lines here. And the y equals 1/9 dotted line is here. So the vertical lines that we're actually going to use are the x equals 9 line, the x equals 3 line, the x equals Uh-oh. Boy, I did a bonehead thing there. This is not the x equals 1/3 line. We divided the interval from 0 to 3 into 3 equal intervals, subintervals, and we get x equals, where is it? I know I washed the board here. I've got to have some damp cloth. I'm going to make that legible. This line should have been the x equals 1 line. What I labeled as the x equals 1/9 line should have been the 1/3 line. So here's x equals 1, and here's x equals 1/3. I'm not going to be able to draw the x equals 1/9 line. I'd have to divide the interval between the y-axis and x equals 1/3 into 3 equal parts. If I had a fine point pen, I could do that, but with chalk, it's going to be impossible. So you're just going to have to understand that x equals 1/9 is really close to the y-axis. All right, so we're going to go ahead and plot these points. And the first point we're going to plot uses x equals 1/9 and y equals -2. We don't have the x equals 1/9 line, but I'm going to go ahead and make a couple of little marks down here between the x equals 1/3 line and the y-axis to divide the thing into 2. And maybe I will say, okay, this is not totally accurate. This is my x equals 1/9 line. Here. And we're going to make a point. Okay, so we're going to put a point right here. Where the x equals -2 line meets the x equals 1/9 line. Very close to the y-axis. So close that the point's going to just blob over the y-axis, but it's still going to be a little bit to the right. Then the x equals 1/3 and x equals -1. So the x equal or the y equals -1. The y equals -1 line meets the x equals 1/3 line. Then the x equals 1 line meets the y equals 0 line, which is the x-axis. And the x equals 3 line meets the y equals 1 line. So here's the x equals 3 line. Here's the y equals 1 line. And the x equals 9 line meets the y equals 2 line. There it is. And there's the pattern of my log base 3 function. There's more to it. It's a reflection across the line y equals x of the exponential function. And you've seen this before, so I'm not going to draw it, but make sure you take a good look at it. Your book is going to tell you, videos will tell you. There it is. Now, just since we have it right here, remember the equation 3 to the 4x minus 5 equals 6. Okay. What power of 3 equals 6? 3 to the what equals 6? We answer that question by noting where the line x equals 6 meets the graph. And we see that that's at y equals maybe 1.8. Okay? So You know, what I'm saying is ridiculous. I got it backwards because it's real easy to get this backwards. If it's easy to get something backwards, this is my day to do that. So forget what I did. Except maybe not, because I still think what I did is right. And I, no, no, got it wrong. Okay. Anyway, there's the graph of a typical logarithmic function. And let me pause for a minute just to make sure I'm giving you information that's going to help you as much as possible with the homework. Okay. Wanted to just take a quick look at your homework to make sure I'm giving you information that's going to be useful to you. Um, so our log base 3 graph, okay, here's a graph of y equals log base 3 of x. Here's the x equals 1 line. Here's the y equals 1 line. What would the graph of y equals log base 3 of x minus 3 look like? Well, what kind of transformation do we have? We'll talk about this for a second. Okay, so and I'm going to change this. I don't want too many threes in there. I'm just going to do x minus 2, just changing the problem a little bit so we don't confuse the threes. Okay. So y equals log base 3 of x minus 2 is transformed from the log base 3 of x. X has been replaced by x minus 2. So the graph shifts 2 units horizontally, which would be 2 units to the right. Okay. Now, if x equals 1 here, the vertical asymptote of the log base 3 graph is the y-axis, and that's going to shift. The vertical asymptote is going to shift 2 units to the right. Okay. Shifts from x equals 0 to x equals 2. Okay, so here's the original vertical axis. The asymptote. Here, it shifts 2 units to the right. That would be over to line x equals 2. Hmm. So you have a rightward shift of 2 units, and the graph will then have its asymptote at this line, and we'll come up here. It's going to have the same shape as the original graph. It's just everything's going to be 2 units to the right. Every point moves 2 units to the right. 2 units, 2 units, 2 units, and so forth. Now you really need to review the basic transformations. Okay, so let's look at a couple more. I'll just stick with a graph of 3 to the x for right, or log base 3 graph for right now. Okay, so there's kind of the bones of this graph. What would the graph of g of x equals 3f of x look like? How would the graph of 3f of x compare with the graph of f of x? Again, for some reason, this is hard for students. And it's pretty much all students. So if you're not completely getting it, again, you got to review it and keep thinking about it. How does a graph of 3f of x compare to the graph of f of x? Well, take a value of x and plug it in here, okay? And you're going to get a y value. Take the same value of x and plug it in here, then you're going to get a y value for that that's the same as a y value for this. But then you're going to multiply it by 3, okay? So let's just make it real explicit. I'm not even going to say plug in. I'm just going to say, let's find f of 9. f of 9 equals 2. Because 2 is the power you'd raise 3, to which you'd raise 3 in order to get 9. 3 to the second is 9, so the log base 3 of 9 is 2. Questions? What is the value of g of 9? Well, g of x is 3f of x, so g of 9 would be 3f of 9. Okay? Which is 3 times 2, or 6. No matter what the value of f of x is, the value of g of x is 3 times as great. So any y value you get for f of x, let's make sure we understand that this is a y value. Okay, find f of 9, you get y equals f of 9 equals 2. So y equals g of 9, which is 3 times f of 9, would be 6. 3 times as great. So the values times the y values of f of x, which means that we could take some y values. Right there's a y value for this value of x. What is x there? It looks like maybe 0.4. It doesn't matter. This is some value of x. This arrow represents the value of f of x, right? And we could take a bunch of other x values just anywhere we want. And these arrows represent the y values. Of f of x. Say the yellow arrows, you can, unless you're colorblind. Okay, these arrows represent the y values of f of x. It should be obvious which arrows those are. Okay. Now, what are the arrows for g of x going to look like? They're going to be 3 times as long. Okay. So right here, right next to the arrow for f of x, I'm going to make an arrow that's 1, 2, 3 times as long. And this will be a point on the graph of g of x. I'm going to do the same for the rest of these arrows. This arrow is this long. I'm going to go that far and that far. So I'm going to go up to about here. This arrow is this long. So I go 1, 2, 3 times that. Probably put me up about here. This arrow, 2, 3 is going to take me up to about the top of the board. So I can't go any higher. But here I've got a bunch of points on the graph of g of x. So I should be able to sketch it. Now, the other thing is, this point here is right on the x-axis, the point 1, 0 on the graph of log base 3 of x. If I multiply 3 by 0, I still get 0. So the other graph will also go through the origin. So I'm going to have a graph that looks like this. It's getting shallower. By the time we get out to the end, it's going to be up, about that high above the blackboard. It's going to look similar. And if I draw a smaller graph, this is my graph of f of x, my graph of g of x, kind of look like any vertical line that I draw. The graph of g of x should be 3 times as high as the graph of f of x. And I didn't make it high enough. It's the way I've drawn it, it's more like 2f of x, but you get the idea. Well, let's move to a different topic or different aspect of this. What's the domain? Of y equals log base 3 of x. Well, the domain is all the possible x values, right? If we go back to the table, I'm not sure I can find it. Yeah, okay. X is 2, 3 to the x is 9. X is 1, it's 3. So I'm cutting it down to a third. Every time my x value goes down by 1, my y value becomes 1/3 of what it was before. So a third of 9 is 3, a third of 3 is 1, a third of 1 is 1/3, a third of 1/3 is 1/9. Okay? Meaning each of these y values is going to give me a point that's 3 times as close to the x-axis. Now this is for the 3 to the x function, not for the log 3 function. Okay? If I look at the log 3 function, my values of y are 2, 1, 0, -1, -2. My values of x are 9, 3, 1, 1/3, 1/9. Each one is 1/3 what the other one, what the previous was. Okay? That's 1/3 the value of the previous number. So we could keep going. We could keep going x values in this direction. Next one would be 1/3 of 1/9, which would be 1/27. Next would be 1/3 of that, which would be 1/81. Next would be 1/3 of that, which would be 1/243. The next would be 1/3 of that, which would be 1/729. And now I'm going to start making mistakes. If I try to triple 729, but I think we're going to get 2187. Okay, but don't quote me on that. Normally my brain could do that pretty easily, but kind of a foggy morning for me. Okay. Now the idea there is not the mental calculation. The idea is no matter how far I go, no matter how many times I take 1/3 of the previous value, I'm still going to have a positive value, right? I'm never going to hit 0. If I want to go 1/3 of the way to that wall, and then 1/3 of the way from there, and 1/3 of the way from there, theoretically, I never get to the wall. Although some part of me is probably going to smash into the wall if I try it. Okay, so I'll move slowly. Okay, well, That's why this graph is to the right of the y-axis. All the x values for the log function have to be positive. You can't do the log of a negative number because no exponential function has a negative value. Exponential functions have an asymptote at the x-axis. Logarithmic functions have their asymptotes at the y-axis. So, not sure why I set this board down here, but I did. Domain of y equals log base 3 of x. All your x values are to the right of the vertical asymptote at the y-axis. Now there's more. I got to also say, for any value, any positive value of x, you can find the logarithm. So domain is the interval 0, infinity. Okay, we'll keep that in mind. What's the domain of y equals log base 3 of x minus 2? You remember the graph that we constructed? Y equals log base 3 of x. If x equals 1 here, and x equals 3, maybe about here. Then log 3 of x minus 2 shifts to the right 2 units. So the vertical asymptote, which was the y-axis, shifts to the right. It's a little hard to read, but this is a graph of y equals log base 3 of x minus 2. Uh-oh. You know, when I wrote the domain, I was really careless, I think. When I wrote the domain of log base 3 function, I wrote it with a closed bracket on the 0. Remember that when we do the table, x never gets to 0. That was the whole point of talking about what happens when you keep taking 1/3 of x. It never gets to 0, so 0 is not in the domain. So I started to write another closed bracket. Realized I was writing without thinking. So the domain would be 2 to infinity. Now you can do that algebraically. Let's say reasoning symbolically. The domain restricted by the fact you can't do the log of any number which is less than or equal to 0. So x minus 2 has to be greater than 0. Thus, x has to be greater than 2. I know log base 3 of x minus 2 is the interval to infinity. Okay, well, what about this? How about the domain of y equals log base 7 of 3x plus 12? We could try to construct the graph of this thing. You would have a horizontal compression by factor 3 and a horizontal shift of 4 on a log space 7 graph. We don't even want to try to draw that right now. Okay. Someday you might need to draw it. Hopefully you'd be able to figure it out because it's very similar to what we've done, but the graph would be a little bit, well, the scale would be kind of unmanageable. So anyhow, we're not going to worry about that. We're not going to try to construct it graphically. Graphical construction makes sense out of our reasoning here, but also just the numerical reasoning. Our x values can never go negative when we're constructing the table. The x values of the log function will never be negative because the y values of the exponential function will never be negative. Restriction, very simple. 3x plus 12 can't be negative. Same reason, x can't be negative for this function, or x can't be less than 2 for this function. 3x plus 12 greater than 0. Subtract the equation negative 12 equal, or add the equation negative 12 equals negative 12. You get 3x greater than negative 12. Divide both sides by 3. And you get x greater than -4. So the domain is the interval -4, infinity. Okay, you're gonna see questions like that. Shouldn't have any trouble with them. Okay, well, timed that pretty well. Right now it's time to quit class. And unless you got a question, we're gonna go.